This problem is on buck DC-DC power converter. A buck DC-DC converter operates with the following specifications. Vin equals 100 volts DC, L equals 30 microhenry, C is large. That means we are assuming that output voltage under steady state is constant with very little ripple. D equals 0.3 and Fs, the switching frequency, equals 50 kilohertz. The full load current I0 FL equals 21 amperes. This is the output current. And the no load current I0 NL is 3 amperes. No load does not mean that the load has been removed. No load simply means here the minimum load current that the load is taking from the converter. Part A of the problem is at I0 FL and at I0 NL to determine the mode of operation, whether it is in CCM or DCM, and also to find the output voltage V0 at these two currents. First, let's do the mode of operation. TS, the switching period, is 1 over Fs, is 1 over 50 kilohertz, is 20 microseconds. We derived an equation in 2A3 for boundary output current, I0B. I0B is given by V in Ts by 2L, d times 1 minus d. We can substitute for V in Ts, L, d, etc. And evaluating this, we will get 7 amperes. So the boundary current is 7 amperes. This is the current at the boundary between CCM and DCM. So if the output current is more than this boundary current, it is CCM. If the output current is less than this boundary current, it is DCM. So at full load, I0 FL is 21 amperes, which is more than 7 amperes. So that is CCM. At no load, I0 NL is 3 amperes, which is less than 7 amperes. So it is DCM. So it's a very straightforward application of the boundary current idea. We can also approach this in a slightly different way. We will see that next. The same thing will again determine whether the operation is in CCM or DCM. First, let's assume CCM operation. Once we assume CCM operation, we can calculate the delta IL, which is the peak-to-peak ripple current. This peak-to-peak ripple current is given by V in Ts by L d times 1 minus d. We can substitute the values of V in Ts, L and d, and we will get this. Calculating this, we will get 14 amperes. This figure shows the inductor current waveform under continuous conduction mode. We went through this in 2A1 video. Delta IL is the difference between I2 and I1. We derived the equation for delta IL in 2A1 video. The average of the inductor current is the output current I0. The difference between I0 and I1 is delta IL by 2 because I0 is exactly in the middle of I1 and I2. I have marked delta IL by 2 here. From the figure, you can see that delta IL by 2 cannot be more than I0 because under CCM, I1 cannot be 0 or less than 0. So for CCM operation, delta IL by 2 must be less than I0. If delta IL by 2 is more than I0, then it is DCM. I0 FL is 21 amperes, which is more than 14 by 2, so that is CCM. I0 NL is 3 amperes, that is less than 14 by 2, so that is DCM. So we can think about it in this way also. There is one little point here. Delta IL by 2 is in fact the boundary current. The boundary current is V in Ts by 2L d times 1 minus d. Delta IL is V in Ts by L d times 1 minus d. So delta IL by 2 is I0B. We have used this for the derivation in 2A3 video. So delta IL by 2 is IOB. Even though we seem to be approaching in slightly different ways, we are practically doing the same thing. Next, we will find the output voltage V0. The formula to be used will depend on whether we are dealing with CCM or DCM. Under full load conditions, 21 amperes, we showed that the operation is in CCM. And when the converter is operating in CCM, V0 is dVin. So duty cycle is 0.3, Vin is 100 volts, so V0 is 30 volts. We will next find the output voltage under no load current conditions. I0 equals I0 NL equals 3 amperes and the operation is in DCM. We just now showed that. We will do this by using the normalized output voltage equation. We are considering base V in normalization. That is, the voltage normalizing factor is V in and the current normalizing factor is Ts V in by 2L. We have introduced this normalization and these equations in 2A3 and 2A4 videos. ION-NL is the normalized no-load output current. ION, the N subscript stands for normalized variable. So ION-NL is IONL divided by the normalizing factor TSVN by 2L. That is 3 by 20 microseconds times 100 by 2 times 30 microhenry. And that value is 0.09. The equation for the output voltage in DCM under base Vin normalization is given by VON equals VO by Vin. Vin is the voltage normalizing factor. That equals D square by D square plus ION. This equation has again been derived in video 2A4. We can calculate VON value by plugging in D value 0.3 and ION value 0.09 and that is 0.5. So the normalized output voltage under no load conditions is 0.5. So the output voltage under no load condition is 0.5 times 100, 50 volts. So you can see that under no load conditions, when the operation changes to DCM, the output voltage shoots up to a higher value. In this series, there are YouTube videos on this topic. If you are not familiar with the equations and the method that I am presenting, you may wish to go through some of them. At ROS_classroom, that is the YouTube channel, there is a playlist 2A for buck DC-DC converter. The explanations for the operation of the converter are given in these videos in greater detail. Next, we will move on to part B of the problem. What is the percentage voltage regulation? Percentage voltage regulation is given by V0 no load minus V0 full load by V0 full load times 100%. Here, of course, no load, we are taking it to mean the minimum load that the load is imposing on the converter. V0 full load is 30 volts. V0 no load is 50 volts. So the voltage regulation is given by 50 minus 30 by 30. That is 66.7%. That's pretty poor regulation. When you decrease the load from full load to no load, the voltage will go up by 66.7%. Next, we will see part C. Show the operating points at full load and no load on the plot of normalized DC characteristics. The normalization is done using base Vin method. First, let us determine the normalized operating point. The normalized operating points here refers to the pair of values, normalized output voltage and normalized output current. Vn is the normalizing factor for voltage, that equals Vin equals 100 volts, and In is the normalizing factor for current, that equals Vin Ts by 2L, that is 33.33 amperes. You can work it out. So IONL is 3 amperes. So ION NL is 0.09. I am dividing the no load current by the base current. VON NL is the normalized output voltage. VONL is the output voltage. Vn is the base value or the normalizing factor for voltage. So the normalized output voltage is 50 by 100, that is 0.5. This pair of values 0.09 for the normalized current and 0.5 for the normalized voltage. It represents the operating condition under no load. In a similar way, we can find the operating condition for full load. IONFL is IOFL by IN, that is 21 amperes divided by 33.33 amperes, that is 0.63. Also, VONFL is VOFL by VN, that is 30 by 100, that is 0.3. The normalized current of 0.63 and the normalized voltage of 0.3, they represent the operating condition under full load condition. So I0NL equals 0.09 and V0NL equal to 0.5. That is the normalized no load operating condition. I0FL and V0FL, they represent the normalized full load operating condition. Next, we will plot these operating points on the normalized DC characteristics. This gives the buck converter DC characteristics. This is the complete DC characteristics of the converter under CCM, boundary and DCM condition. A full explanation of how these characteristics are arrived at, you may find it in video 2A5 in this series. This plot shows the complete normalized DC characteristics of the buck converter using base Vin normalization. The plot gives how the normalized output voltage VON varies with the normalized output current ION for different duty cycles D. Each colored line is for one duty cycle all the way from D equal to 0.1 to D equal to 0.9. We will mark the full load operating point on this graph. Since D equal to 0.3, the full load operating point will be located on the D equal to 0.3 curve. That is the blue curve, the third curve from the bottom. The green dot shows the operating point under full load condition. The X value is 0.63. That is the ION full load value. And the Y value will be 0.3. That is the normalized output voltage under CCM condition. Now we will mark the operating point under DCM condition. Here the X value ION no load is 0.09. That is the no load normalized current. And the Y value is 0.5. That is VON NL. That is the normalized output voltage under no load condition. So you can see clearly as the load current is reduced from full load value until the operation hits the boundary value, the regulation is very good and the regulation becomes very poor in the DCM region. Lastly, we will see part D. Find the value of D such that V0 is regulated to 30 volts at no load. Here what we are doing is we are changing the duty cycle so that the output voltage is no longer 50 volts but comes down to 30 volts once again. That means it comes back to the full load value even under no load condition. So let's find the new D value. Let's use the normalized voltage equation again. VON, the normalized output voltage, using base Vin is D square by D square plus ION. We can solve for D. D square is VON ION divided by 1 minus VON. So D equals square root of VON ION divided by 1 minus VON. ION under no load is 0.09. So we want to adjust the duty cycle such that VON becomes equal to 0.3. Taking the value of VON as 0.3 and ION as 0.09, we will get the new duty cycle as 0.196 or almost 0.2. So if instead of 0.3 we change the duty cycle to 0.2, the output voltage will go back to the value of 30 volts even under no load condition. We can show this on the plot. So new D value is 0.2 and the curve we are on is D equal to 0.2. So that means it is the second curve, the green curve from the bottom. ION is 0.09. So if you reduce the duty cycle to 0.2, the operating point changes as we saw, and the normalized output voltage will be 0.3 and the actual output voltage will be 30 volts. So this is what a controller will do when the load current is reduced to 3 amperes. It will drop the duty cycle so that the output voltage is maintained at 30 volts. That's the end of this problem video. If you like this video and this series of videos, please subscribe to this channel and click the like button. Thank you.